A particle of mass 1 kilogram. So once you read that right away, 1g straight down. Thank you very much. Strings of both length 1 meter each. This is 1 meter. This is 1 meter. This means isosceles triangle, 2 angle A's. Okay. Now it says 2 strings. 2 strings means 2 unique tensions. T1 acting up this direction here, T2 acting in this direction here. The other end of the second string is tied to a ring of mass 3g, or 3 kilograms. So this ring here is going to be going down at 3g. Now, to have a closer look at understanding the ring, I'm just going to do a quick diagram for you. So this is just zoomed in view of the ring. Okay, and what happens is you have something pulling on it. So see the way the ring is currently being pulled on. So it means that it's tethered around the ring and it's pulling on it. Okay, and that means that there's going to be a reaction force at play. Okay, so do you know where the ring is situated on the pole? Did everybody agree with that? So the ring is wrapped around a pole of some sort. So because that's pulling it, the ring is eventually going to make contact with the pole. So you can see that they're now in contact with each other. Basically something like that, yeah? And basically reaction force R in that direction there. Is everybody happy enough with that? So basically that, okay? Now, so we have a reaction force R holding the ring in place. Now, can anybody tell me something about the direction of R? Does it stay in the one direction or is it going to be constantly changing? Remember that the whole system here is basically so what we're getting at there is that this here will just be I won't rotate that. This here is just going to be constantly changing direction around the ring, so that the value of R remains the same. However, the direction R is in will change. Okay. Now the second thing you need to know is the faster you go, the faster you can swing this around. What happens to the angles A? Sorry? I'd actually argue that they will. So, what is that?
They're unextensible, so when they say the same.
They're unextensible, right? So it has to probably be in the middle, one on one. Okay? But the ring, is the ring movable? Did you say the ring's movable? Ring is fairly below. So the ring just maneuvers itself into a position that they're both the same, so they're about 1 meter each, okay? That's sorry? Yeah, you would, yeah. I'm just trying to get at that the ring can move up and down, but because they're inextensible, the ring will eventually just find a spot where both of them are stuck at 1 meter. Okay? Now, what to do, okay? So, what we're going to do first is we're going to resolve some tensions, okay? So we have T1 going this way, and we're going to have T1 cos A, T1 sin A going up and across. Then we're going to have T2 going down this direction here, and T2 is what's T2 doing? It's going to be A is here, isn't it? Oh dear, excuse me, mixing myself up there. The alpha's at the top, so that's going to be cos A and sin A the opposite way around. Excuse me, cos A, sin A. Now that that's done, what we have next is we're looking at this here. Going to the right is T2, sin A going directly up, T2, cos A. Now these tensions are written relative to. Oh, you're right. It is going downward. Excuse me. Yeah. T2 cos A is going downward. These are written relative to the particle. one of the ropes is pulling it down to the right, the other rope is pulling it up to the right. Okay, so that's the way tension's acting. Okay, now we also have our 3G going down from the ring's perspective and our 1G going down from the particle's perspective. So let's do the 1 kilogram particle. Once again, motion in a horizontal circle. F up equals F down, okay, and FC, are we using mr omega squared again? 14 radians per second, sounds like angular velocity to me, mr omega squared. So look, you're on a winner now, okay? So, forces up versus force down, what's going up for the particle? T1 cos A on its way up. And what's on the way down? T2 cos A plus 1G. Okay, what about part 2? FC, what's driving it towards the centre of the circle? Driving it towards the centre of the circle? What force is driving towards the centre of the circle, guys? Come on. T1 sine A and T2 sine A. T1 sine A plus T2 sine A equals mr. M is 1, isn't it? Mass of 1. R, radius, anybody? Do we know the radius? I think we do. Okay, so what we have to do here is we have to find out the radius. Okay, we've already decided that we're not going to. Okay, so the radius, 1 meter, A, radius. Get it in terms of sine A because it's all going to be there anyway. So sine A equals r over 1, r equals 1 sine A, otherwise sine A. Is that right? So we're going to get the radius in terms of sine A and cos A. Now the reason you might know to do that is if you look to the left, you already have sine A's anyway. So if you leave r in here, you're just adding a second variable to the equation, a variable that you can quite readily get rid of. So what we're going to do is change r to sine A. And then omega squared, anybody? 14 squared. So what happens is the sine A's cancel. And we get T1 plus T2 equals 196. A very manageable simultaneous equation. Okay. So that there is all for the 1 kilogram particle. So that's that part done there. Okay. Now, what we're going to do next is for the 3 kilogram ring. So guys, can anybody tell me what type of equations can we use for the 3 kilogram ring, guys? Okay. Is the 3 kilogram ring, is it moving in a circular motion or is it just rotating on its own axis like a planet, for instance?
Is it not going around with a pole attached?
Sorry?
Would you go around with a pole attached?
It is, but it's not moving linearly. So an example would be what we're trying to discuss here, guys, is the difference between your own rotation, your inertia, versus rotation around another object. So if we have a planet, guys, like so, we know that this planet is rotating. We know this planet is rotating on its own axis. Everybody happy with that? So it has its inertia. It isn't moving linearly, so it isn't undergoing circular motion as we would know it. Is that alright? So what we're going to say here is that this here is when you undergo horizontal circular motion, and you can see that it's moving linearly. If we pause it there, it's still rotating on its own axis, but we can't see it move. Therefore, we say the forces are imbalanced there, even though there is rotational energy. Okay, but we don't need to consider that rotational energy for this question. So, what I'm trying to get at there is that the ring is balanced up and down. So you're right about forces up and forces down because the ring isn't moving anywhere. So what's force up versus force down for the ring? Now, from the ring's perspective, 3G is going down. What's going up? From the ring's perspective, the green triangle here reverses direction. It's being pulled up by the tension. Therefore, T2 cos A is pulling it upwards. T2 sin A is pulling it from the left. It's like a tug of war, guys. The side on the left is getting pulled to the right. The side on the right is getting pulled to the left. So when you're in a tug of war, each of you has different perspective. One of you is getting pulled to the right, the other one's getting pulled to the left. This question is no different between the particle and the ring. Do you have a different relationship with the tension? Different directions. Okay? So, what's F up then, guys? F up? Anybody? Just T2 cos A. Now, there's another equation we can do for this. Can anyone tell me the other equation? It's in balance, it's not moving left or right. It's rotating, but it's not moving left or right. Yep.
Would not be 3G minus T1 cos A?
No, because see the T1 cos A? Yeah. It's not connected to the ring. T1 cos A is connected to the particle, and through the particle, T2 is acting. So unless it's directly connected to the ring, unless that string is directly connected to the ring, it can't influence it. Or the influence is observed through T2.
Is there any tension on the wire?
Here? Yeah. That's sort of considered like a rigid bar or something like that. So it's relatively unaffected, just stays in position and everything rotates around it. Okay? So, just give me a minute with this. Yeah, so forces left equals forces right because it's not going in any particular direction. So what you said there, R going to the right equals the force going to the left, which is T2 sin A. Okay, what does the question want us to do again? Find the tension in each string and the angle which the strings make with the vertical. I have to find A and I have to find T1 and T2. I did not have to find R. I don't know if I need R yet, but I don't have to find it. Okay, so let's see what we can do here. So, T1 plus T2 equals 196. So, what we have here, guys, is more alert than I am. Okay, so that's A, that's equation B, that's equation C, that's equation D. So what he's saying is introduce C into A for all the cos A's, isn't it? So what we can get here is this. We can get a T2. Sorry, just for T2 cos A really. So T1 cos A ends up to be equal to 3G plus 1G. Yeah? Is that what you're suggesting? Yeah. And then T1 cos A equals 4G. Okay, so that's T1 cos A equals 4G. What we're going to do? I want, because I have this equation here, I want T1 in terms of T2. That would really work well with this equation here. Okay, so what I'm going to do here is I'm going to get G on its own. I'm going to say G equals T2 cos A all over 3. I'm then going to take it, that's equation C. I'm then going to combine equation A and equation C to become T1 cos A equals T2 cos A and then plus 1G, which is now going to be T2 cos A over 3. Now that was a lucky break there because all the cos A's cancel. I'm going to get T1 equals 4 over 3 T2. Now I have T1 in terms of T2. I can bring down this formula here to T1. See the way it's 1 T2 here? Yeah. Plus a third T2. It's 1 plus a third. Which is 4 over 3 T2. Shh, lads, music's quiet now. Okay, now what we have here, guys, is we're going to sub it in. So we're going to get 4 over 3 T2 plus another T2 equals 196. Add them together and we should get 7 over 3 T2 equals 196. So can somebody in the class divide 196 by 3 sevenths, or sorry, by 7 thirds I mean. 196 divided by 7 thirds? 84. Plug that back into this equation here, where T2 is now 84. What's 196 minus 84? Because we bring the 84 to the other side. Sorry? 112n. Okay guys, so what we've done there is we found 112 and 84 newtons for T2. We now need to go back to an equation to find the angle. We know T2 cos A equals 3G. So T2 cos A equals 3G. T2 is 84 cos A equals 3G. Cos A equals 3 multiplied by 9.8, because that's what 3G is, divided by 84. What is cos A, guys? Point 0.35. And cos inverse 0.35? Shh. Cos inverse 0.35? 69.5 degrees. Okay guys.